Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. We'll be taking a look at this very interesting optically isolated probe set. This is the XFVP from Saker, which is a galvanically isolated probe configuration. Now, what does that mean? It means that we have a probe head here on the right side and a probe body on the left side, and the only connection between these two is a fiber optic that runs between them, nothing else. So they're fully galvanically separated from each other. The probe body itself can then be connected to an oscilloscope or spectrum analyzer via a regular connection, and whatever you need to connect to the other end of this SMB connector, which we will talk about. Now, there are some immediate obvious advantages here. You could have your probe head floating tens of thousands of volts above the reference ground of the instrument you want to connect the body to, and there'll be no danger because you have the fiber optic connection between them. And you could, of course, put this in a safe place. You could elevate it from the ground so that there's no arcing. And there's some really cool things you can do and some very difficult measurements that this enables. We'll get to that in a second. Now, the concept of connecting things with a fiber optic is, of course, nothing new. Our entire telecom industry is based on this phenomenon. Photons travel really nicely in fiber optics and they can go very long distances, and we take advantage of that to make our fiber optic connections. So here's an example of one of these devices that's used in our telecom industry. This is a single mode fiber operating in a 1550 nanometer, and this is just a simple detector. This just converts the photons from one side and puts out electrons on the other side. And looking at this connector, this is a V connector, which means that this thing has 50 gigahertz of bandwidth at least, which means very, very high frequency and very high speed, which is of course what we want from our fiber optic connection. So this is a really common technique of converting electrons to photons and back to enable a lot of applications. And you've seen other reasons why this is useful. This is just a basic power supply, and all of these power supplies are going to have an optocoupler, opto-isolator in the middle, which is exactly the same situation. You're separating two nodes from each other by only connecting them with traveling of photons between them. And that's very useful again because you want to isolate and protect the two ends of the circuit, so therefore you have a different reference ground. So we see these kind of features all the time, but what makes it difficult to put in a probe? Well, in a probe, what we're trying to optimize is very different. We want to basically reproduce the analog signal appearing on one side to end up here with as much fidelity and linearity and dynamic range as possible. That's not necessarily what we're worrying about, let's say in an opto-isolator or even in our telecom industry, although nowadays we're really pushing the limit on that as well. So therefore, optimizing this for that kind of SNR and for the kind of applications, let's say an oscilloscope needs, is going to be pretty important and pretty difficult. So let's take a look and see how well this performs, and we'll also take a look inside of it. And of course, this is an active probe set, meaning that both the probe head and the probe body need to be energized in order to perform the electro-optic and optoelectric conversion. There's amplifications and signal conditioning required to make sure this thing works. The probe head uses two AA batteries. Nice, it's quite common. I'm glad that they're not using a 9-volt battery, and this will last a very long time on those AA batteries. And the probe body itself has a USB connection, which you can connect either to the oscilloscope, spectrum analyzer, or a battery pack and run the whole thing from that. It will last also a very long time. One of the really nice features of this is that it does have the calibration capability built into it. Remember that when you connect this to an instrument, it is completely instrument agnostic. So you can connect it to any brand of oscilloscope or any spectrum analyzer, and this has to work. And the calibration button has a bidirectional connection over the fiber between these two devices, and it performs the DC offsets and gain calibrations and so on by applying the appropriate signal automatically internally and then detecting on the other side. So it's pretty sophisticated and makes it completely standalone, which is fantastic, because if you have to adjust things on the fly, it's going to get pretty frustrating. And this gives a lot of confidence on the measurement that's being made. Now, this thing does support up to 250 megahertz of bandwidth, which is fantastic. So pretty good rise and fall times, which is required for the new generations of gallium nitride DC-DC converters that do have a very high frequency and sharp edges. So you should be able to characterize that with this reasonably well. The input is an SMB connector, like so, and it is touch protected, which makes sense because this is the business end, which can have tens of thousands of volts on it. And it can do plus or minus 2.5 volt at the input, 1 mega ohm, about 0.8 picofarad of capacitance, which makes sense consistent with the kind of frequency response it's expecting. And it is a times 10 probe, which means that as soon as you connect this to it without any attenuation here, this acts like a times 10 probe. But if you want to measure really, really high voltages, it does come with several different dividers, which all just directly plug into this nicely shrouded SMB connectors to further protect it. And then we have this is a times 10, we have a times 2, and a times 500 for big attenuations. And you can see the box is bigger. We should take a look inside on these and see how they are made. So overall, really easy and straightforward to use. So let's put it to the test. So let's take a look at inside these modules. This is the receiver module connecting to the oscilloscope side, and you can see we do have our coaxial 50 ohm line leaving this module. We do have 2 fiber going in, and that kind of explains how the bidirectional interface actually works. I'll explain that in a second. And this board was also here, which is nothing more than the user interface and a couple of LEDs. So I've already removed that, but look, you see there's a tape here so that it either doesn't rub against the sharp edges and damages the fiber over time, or it doesn't make any electrical connections. These are nice attention to details. Very cool to see. Now this thing, as I said, does have a bidirectional fiber connection for the calibration and so on, sending messages back and forth. That's a digital interface in a sense, and looks like that they have made a custom little interface there. Kind of clever, nice Spanish engineering. And this fiber with a fairly large aperture just plugs into that, and underneath it we have a pair of transmit receive detector and emitters there, which is used to do the digital communication. Pretty nice and clever. We do also seem to have a lens that's custom made with the fiber coming in, focusing it into the photo detector. This also seems to be something that they may be polishing and making themselves. And this fiber is only one direction. The light coming over here carries the analog information up to 200 megahertz that you're interested in saving. So that just shines in there, and they need to convert that to electrical. A couple of kind of DC stuff going on over here from the power supply, nothing unusual. Now underneath this, we should see some more mixed signal, which we do in fact. Here we have a Cypress SoC. It does have ADCs and DACs in it, which they may be using in combination with some other circuitry to do the calibration, as well as some gain adjustment. The connection directly is on the board over there. And this is an Analog Devices 88001, which is a line driver. It's actually a current mode feedback amplifier, which is nice because it can interface with the photodetector reasonably easily. And then from there, you will have a lot of current driving capability to drive this coax into 50 ohm. Now this part is rated at 5 megahertz for 65 dB C of THD, which is pretty good, and that means that it's going to maintain the linearity. We'll have to take a look at the noise of it as well, see how much noise this puts out, because there is quite a bit of amplification that does happen there. But look how nice it is. A lot of custom made components in there. It's not easy to replicate something like this, and I think it's a very small team that have put this together. It's quite impressive. And here's what we have inside of the probe head itself. As you can see, it is powered by a pair of AA batteries, and we do see a mirror of that custom package over here, which brings our bidirectional digital signal over fiber here on the other side going into this board at the bottom, which probably does have its own microprocessor. I'm not going to remove this because it's a little bit tricky to remove it because of the fiber connection over here. And we do see the fiber interface from the transmitter emitter over here. It's already shrink wrapped. Now the analog signal coming over here goes through the cage, and the very first thing it sees, it does a latching relay, and this has to be latching for obvious reasons because this is battery powered, of course. Now there are a few other analog switches in the way which allow the input to be connected to 0 volts to a reference voltage or the input, and that's part of the calibration procedure. There is also an Analog Devices AD4817, which is a low noise 1 gigahertz op amp, so the system bandwidth is certainly not limited by that, but it does provide a very nice input impedance, which is of course what is going to be seen by this external voltage here, which is pretty important. And then afterwards, the signal, once it's conditioned by that, it goes through the emitter, and then the fiber leaves this. A lot of care taken to make sure that this thing works the way it's expected and maintains the dynamic range of the signal, which is the very first thing we're going to measure. And here is what's inside of the 500X divider. I've also removed the cage from that, and you can see that underneath the cage they do have a little bit of a tape to provide a bit of additional protection. This is hermetically sealed. The input of this is a 10 mega ohm in parallel with 15 picofarad, and it is difficult to divide this and still maintain the frequency response. And there is also a capacitor in here towards the signal side, towards the instrument side, and that allows you to adjust and perhaps flatten the frequency response a little bit more. The slits in the PCB are filled with epoxy, which probably doesn't make much of a difference, but you do have the division across multiple resistors over there to slowly bring the voltage down and prevent arcing and so on. There's also capacitors in there, and this entire thing has to be very, very carefully designed. It's not easy to divide something from 2000 volts down when you do have to maintain a high frequency response through it. It's all custom made, of course, by the team. So let's take a moment and appreciate the difference between something like a classic differential probe and an isolated probe. Now, differential probes can be used to measure things that have tens of thousands of volts on them, even with respect to the ground. And this is accomplished by applying the appropriate attenuation on both the positive and negative input of the differential probe, which means that common mode signals do have to experience the same attenuation, and that's because you have this ground in the middle, which is the reference ground of the instrument, and you do have to attenuate everything down in order to bring it down to a level where you can interface safely with the unit. As a result, you have a lot more components that you need to worry about, and the matching between these components and the nonlinear effect between them across very large common mode, especially fast changing common mode signals, will lead to poor common mode rejection. But in an isolated probe like this one, the entire structure is floating. This ground is not the instrument ground and is not the earth ground. You can in fact reduce that amount of coupling to the earth ground by elevating this entire structure above ground. That's what that tripod is for. So you will have, for example, a capacitor over here that will go into the ground over here, and that capacitor can indeed be reduced by elevating everything. And the amplifier really only sees only the difference between 1 and 2, despite the fact that there is no symmetry in the signal here on the right side, and you're moving both the port 1 and 2 up and down together, and only the difference is present into this amplifier. And that's a really important, unique feature of something that is isolated, especially in this single-ended architecture that you see. You obviously have to be very careful, because you could float these things to a certain point where they can arc to the ground or the table you have them, and that's again part of the reason why you have to use the tripod. But up to tens of thousands of volts, even in fast changing common mode signals, you cannot beat this in terms of architecture. Just generally, of course, the optical interface will have some disadvantages over this one, which we will show in measurements, but there's a very big difference in what you can do between these two architectures. So let's do some basic measurements with the probe to get an idea about the SNR and THT limitations it has. As with any active probe, it's going to degrade the signal in some way. It's going to add noise as well. And this is normal, of course, for this probe. This is an electro-optic and optoelectric conversion. I just want to get an idea of what that does. So here we have the Rodenshorst SMBV100B, which we're going to use as a source. We're going to use it at 40 megahertz. Now the probe has a bandwidth of over 200. So with a 40 megahertz input, we would easily see the fourth harmonic if we want to. And then I'm splitting this into two. The reason is because the input impedance to the probe is high, and we do want to terminate the synthesizer into 50 ohms. Now by splitting it over here, I'm able to terminate this into the oscilloscope, which I will show you in a second, and that will be our 50 ohm termination. There's another advantage here, is because by looking at this signal and this signal simultaneously, the one that's processed through the probe can then be compared with the raw measurement, and therefore any of the nonlinearity of the oscilloscope, for example, can be eliminated as far as making sure it's not the limiting factor. And that's going to be quite useful in this measurement, because you really want to measure only the probe. And then here we have the probe that's connected to the oscilloscope. I wish this cable was a little bit longer. Even 10 inches longer would be better. I have to put it on the box here so it's not dangling. And then here at the top, we have the Rodenshorst MX04 series. This is a 12-bit architecture, and when it's used in high definition mode, which is essentially taking advantage of oversampling, we can get 15 or 16 bits of dynamic range, which is way more than we need to characterize the probe. So let's see what we measure. It's really important for us to set the oscilloscope correctly to take the most out of the probe. So let's double check that to make sure everything looks good. Now the probe can terminate into 50 ohms, which is great. In that way, both channels are now actually set to 50 ohm. And if you look at channel 3, that's the channel directly connected to the synthesizer, at 40 millivolt per division. And you can see I've reduced its bandwidth down to 300 megahertz. That's because there's no reason to capture more signal than the probe can provide. It's just going to be additional noise. So I have limited the bandwidth of both channels to 300 megahertz. There's no probe on channel 3, that's to be expected because it's a direct connection. But on channel 1, aside from limiting the bandwidth to 350 megahertz, on the probe I have also defined a 10 volt per volt attenuation, which is the probe's attenuation, because it's a times 10 probe at the end. It's just a simple definition in here. So everything looks good from that point of view. Both channels are at 50 ohms, both are at 40 millivolt per division. Now the probe is right now turned off. As a result, if you look at the time domain signal of channel 1 and channel 3, they're essentially on top of each other. Doesn't make much of a difference, but we can look at the spectrum to get some more insight on the noise floor of the oscilloscope itself. So here's the FFT, or the spectrum of channel 3, and you can see on this that it does start to go down. That's because we're artificially limiting the bandwidth, but we're looking at a displayed average noise level of about minus 80 dBm. Now if I change this, instead of using channel 3, use channel 1, you can see that we'll have about 10 dB or so on average higher. That's because this is a times 10 probe, and the scope artificially boosts this signal by a factor of 10, and that's because it has to do this in order to calculation to make sense. Right now the probe is turned off. Now look what happens when I turn the probe on. We're going to get the noise from the probe as well. I'm going to have to cal that once we turn the probe on, so we can get rid of all the DC. With the push of a button, it does the calibration, which is fantastic. And look at that. So the displayed average noise level went up to about minus 50, minus 45 dBm. And the shape of this noise is the shape of the bandwidth of the probe. And the probe does indeed have more than 250 megahertz of bandwidth, but we will measure the bandwidth of the probe separately. Now you have to wait for the probe to warm up about 10 minutes before you count it, so you get a little bit of drift until everything stabilizes. And that way you get the correct DC gain as well as, of course, the AC gain. So this additional noise that you see is inevitable. That's the consequence of the probe being turned on and being active. Again, this is not a problem, it's just the reality of using these kind of active probes. So now if I go ahead and look at the spectrum on channel 3 one more time, which is the raw spectrum, we can go ahead and turn on a signal, a reasonably small signal, about minus 12 dBm, and we can take a look and see how that looks like on the oscilloscope. So simultaneously we have a very clean signal coming from channel 3, that's directly from the synthesizer, and we're also doing a high definition sampling here. If you look at the sampling under HD here, I'm using a 300 megahertz bandwidth limitation on the oscilloscope, and with the oversampling I'm getting 15 bits of total resolution. That's going to be much more than enough. So you can see that indeed the signal, the raw signal from the synthesizer, is going to look much more clean than the signal coming from the probe, because the probe has some noise added to it, but the signal is pretty small and the probe is times 10. If you look at the THD here, it's pretty good. The synthesizer does a good job, the oscilloscope does a good job. We have a very, very large dynamic range here. Now let's go ahead and change that to channel 1 of the probe. There it is. Now the noise is high enough, the nonlinearity doesn't even show up. So the spurious free dynamic range with the probe is limited. That again is expected. That's nothing unusual there. And I can go ahead and reduce the signal continuously. I can bring it down to, let's say, minus 30 dBm. Right? Well, around over here. I don't think you can make it much more. It's actually clipping a little bit. So you can measure signals that are pretty tiny. It's not a huge deal, but just keep in mind that there is limitation as with any active probe. And of course we can push the probe the other way by putting a signal that's very large at its input, trying to evaluate what it does to the total harmonic distortion. Now the probe with no attenuation in the front can take plus and minus 2.5 volts. Here I'm putting a 4 volt peak-to-peak signal essentially at the input, which is 80% of its full scale. And we can see both of the signals at the same time in the time domain. We see a nice symmetric signal from the orange line here, which is channel 3, directly from the synthesizer. We do have a little bit of an asymmetry coming from channel 1, which is the probe, and that asymmetry is not from calibration, because if I cal it again and wait for it to finish, it's still there. And if I disable the input, you can see it is flat, does have a DC 0 offset. This is some nonlinear effect that is happening, but we are really pushing the probe again. We're putting a very large signal in at its input. Now if you look at the raw THD coming from the synthesizer and the scope itself, we have a signal that's almost 16 dBm, and the second harmonic is at minus 30, which is pretty good. Now we can switch that over to channel 1, and you can see that indeed we do get a little bit of hit in the THD, but it's not so significant actually. The power reported is a little bit higher. That's because the signal does indeed go a little bit below the negative points here, but overall I think it's doing very well. I'm really pushing this probe here. Keep in mind that most people probably don't care so much about this part of the characteristic of the probe, but it's important to understand exactly what it does to your signal. And here's our setup to measure the frequency and phase response of our optically isolated probe. We're going to be using the Siglent Vector Network Analyzer. This is the SNA 5000 series, which I've done an extensive review and teardown of. It's a really great instrument. Port 3 is 50 ohm terminated before going into the high impedance input of the probe head. On the other side, on the receiver, we're already 50 ohm, so we go into port 1. And this allows us to measure the response. I've already calibrated the instrument and have ensured that the measurement plane is right at the edge of these connectors. So if I make it through, I will see a completely flat frequency response, which is great, which means anything we're measuring on the screen, it really is the response of the probe itself. Let's see. And here's the response close up, and indeed the probe does have the 250 megahertz of bandwidth, and it has reasonably good ripple. If you look at this over here, this is on a 2 dB per scale. This is S13, basically the response through the probe. We do have minus 20 as a starting point, which makes sense. This is a times 10 probe. That's not been corrected for. We have a very, very small ripple, maybe half a dB at most, and then we do have our 3 dB bandwidth beyond 250 megahertz. Now the 50 ohm terminal of the probe body itself is well matched. You can see up to 250 megahertz. We are below minus 10. And look at the phase response. It's really nice and linear. This is a good sign, which means the group delay will be quite flat, and this would have a good faithful reproduction of broadband signal coming in. But I am happy to see that the response is flat. And this is important because remember, this is not corrected for, and therefore whatever you put in there on any instrument, you have to be able to live with, and this is pretty good. So it does indeed meet this spec. Now let's go ahead and try and measure something that we would encounter in the real world, something that is very difficult to measure or impossible to measure unless you do have some kind of an isolated probe. So this is the schematic of a gallium nitride evaluation board by Infineon, which is used for DC-DC converters. These gallium nitride devices, these are high bandgap semiconductor material with very, very large breakdown voltages and very small on resistances, excellent for high efficiency DC-DC converters. And this is a 600 volt device. Don't worry about the complexity of the schematic, that's not relevant here. We were just going to talk about specifically what makes the measurement point very difficult. So the input of this is a pulse width modulated signal, which we can use an instrument to apply, and that's going to be essentially the pulses that appear at the gallium nitride devices. And we have two of them. We have one over here and one at the bottom, and these are sitting at the high side and the low side of the power supply. Now the power supply coming into this system can be hundreds of volts. It can go up to 400, 500 volts because these devices have very large breakdowns. So the issue becomes, how do you measure the gate source voltage of these devices? Because in this situation, the difference between the gate voltage and the source voltage can be maybe up to about 10 volts. But both the gate and source voltage are swinging up and down in common mode hundreds of volts between basically 0 to the VDD voltage, and which means if you want to measure the gate source voltage, you have to ignore that massive fast changing common mode signal. It basically becomes impossible to measure with anything else, and you can imagine how dangerous it would be if you're not careful in how you handle your power supplies. Now there's another test voltage port over here for the device on the low side, and here the voltage is with respect to ground, so this signal can go way up above VDD as well. But in this particular case, the high side one is a very challenging measurement. So let's go ahead and build this and put all of our setups together so we can use an external power supply, and then we can change the power supply voltage, 50 volts, 100 volts, 300, 400 volts, and see if we can maintain that nice view of the gate source voltage and see of the subtle minor differences between that as the device goes in and out of various conduction regions. It's a very complex topic for DC-DC converters, and this waveform, the analysis of this waveform is key in understanding of the efficiency of these kind of devices. So it's a very important measurements to make and very important characterization, and this is why this Infineon evaluation board specifically brings out these voltages so you can study and understand what's the best way to make it. So let's go and take a look at the setup. So let's look at the various elements of our setup with this gallium nitride evaluation board. So this is the back of the board. At the very top is where we apply our pulses or our PWM signals for controlling the GAN gate. And at the bottom here, we're measuring using a regular oscilloscope probe the gate voltage of the low side GAN switch with respect to ground. So here we will see the entire voltage swing. And the voltage measurement here represents roughly the common mode voltage that's appearing on the high side. So we would be able to make some relative comparison and see what we're actually dealing with. And on the other side of the board, we do have a direct connection into the board itself, and that's the high side gate source voltage. So we should be able to ignore the entire common mode voltage and only measure the differential one. We do have a 10x attenuation, which then directly goes into the probe head. And here's our entire end-to-end setup. Now, one item I forgot to mention is that you are able to turn on and off the probe head by using the power button on the probe body. This is clearly an attention to detail done by people who've actually been in the lab, because once you set this up, you really don't want to touch it. You want to kind of leave it alone, and being able to turn it off and on from here is really useful because this is the part that is battery operated. So in the entire setup, you saw the connection between the probe to our board over there. Then we do have just a basic waveform generator over here to be used for the PWM input into the board, and then we do have our high voltage power supply, which goes up to 400 volts. That's going to be the main power supply that controls how much voltage is across the drain with respect to the ground of the gallium nitride devices. And we do have a 5 volt power supply coming from this as a power supply over there. That's just all the logic and the conversion into the GAN drivers. And of course at the top we're going into our Roden Schwarz MX04 series. So let's take a close look at the screen over there. Now keep in mind that in my setup I have put everything really close to each other for the purposes of filming, but having this cable be a fiber cable has another major advantage. The fiber does not pick up any EMF, so if you have inductors connected to this in a DC-DC converter that put out a whole bunch of EMF, especially in laboratory settings where things are improperly shielded, if this cable was coaxial, you will pick up some of that no matter what. But of course fiber doesn't do that, so having this fiber connection from an EMF point of view is a whole other advantage. So let's take a look and see what we have here. I have set the power supply of the system to 50 volts, and we would expect to see that 50 volt appear in common mode across these gallium nitride devices. Now in channel 3, I'm looking at the gate voltage of the low side switcher with respect to the ground. And as a result, you can see on the high side, it goes to 50 volts because channel 3 here is at 100 volts per division. And that's to be expected because this does not represent the difference between the gate and the source voltage, but rather the voltage on the ground with respect to the source. So therefore, you're going to see the entire voltage swing there. Now the same thing is happening on the upper transistor too. Its gate to source voltage is small, but both of them are moving together as high as the power supply voltage. But because we're using the isolated probe, we get to see only the difference between the gate to source voltage and ignore that entire large change in common mode. Now these common mode voltages are pretty sharp at the edges, so we're basically rejecting a really broadband common mode voltage swing there, even though it's only at 50 volts, but I'm going to increase it in a second. But you can observe on the intricate minor changes in the waveform of the gate to source, which is again crucial to understanding the gallium nitride behavior as it goes through various regions of operation and gets saturated and has slope limited or slew rate limited, and you can observe all of that. So let's go ahead and increase our power supply voltage and see what happens. If you see any changes at all in the actual measurement, we're seeing differentially. So here's 50, 60, 70, 80, and here's 100 volts. You can see absolutely no difference in the voltage that we're measuring differentially, which is quite impressive. Let's go to all the way to 300 volts. Here is 310 volts, I believe. Yep. Again, no difference at all. Remember that this huge waveform sitting at 320 volts peak to peak or so is appearing in common mode, but the probe completely rejects it. This is really quite nice. And I should be able to increase it a little bit further even. And here is 400 volt power supply, which is the maximum I can do with what I have. And look at that. That's really incredible. Now let's make it even harder by making the pulse width narrower. Now we really have a very sharp changes there. So let's go ahead and change that. Look at that. That is beautiful. It's difficult to emphasize how hard this measurement actually is under normal circumstances. And the fact that the probe can keep this up and show this with the integrity as it does is really quite nice. So this is just one example. There are many experiments, especially in physics, that you deal with very high voltages and you're only interested in small changes of those high voltages with respect to another high voltage, where all of these things would become quite valuable. And there you have it. I hope you enjoyed this extensive review of the Shahriar isolated probes. If you have any questions, let me know in the comment section. I always like to do these reviews for smaller groups of innovators and engineers because it's very tough to put a product together that competes with other big brands that are on the market. So hopefully you enjoyed this as well and you learned something in the process. As always, thanks to my Patreon supporters, you make a lot of these experiments possible. It takes a lot of time to put these things together, and of course a lot of parts and everything that needs to be purchased in order to make the experiments possible. As always, I'll see you in the comment section.